Welcome to Systems of Equations. In this lesson today, we're going to be answering some of these questions. What are some ways we can solve a system? Is one method better than the other? And what does it mean when you're asked to solve a system? Finally, how many solutions can a system of linear equations have? And the key word there is linear. So let's start with the first one. What are some ways we can solve a system? Well, let's look at a problem. Pause this video and try to solve the system. See which of the methods you remember would be most effective to solve this system. When you're finished, start up again and let's compare. Okay, so hopefully the way you solved this system was through the elimination process. If you'll notice, none of these variables are isolated, and so it would take more work to isolate one of these variables to use substitution. Graphing would be a little bit difficult as well, as these are linear functions in standard form and not slope-intercept. So let's go ahead and do this. Which variable would we want to eliminate using the elimination method? Well, either way, we're going to have to multiply through by some factor in order to eliminate our x's or our y's. Let's go ahead and eliminate the y's. If we want to eliminate the y's, we could make both of these be 15. One of these, though, needs to be negative and the other positive. So I'm going to multiply through here by a negative 5, and I'm going to multiply through on the bottom one by a positive 3. When we do that, we are left with these two equations. So this top equation has just been increased by a factor of negative 5, and the bottom one has been increased by a factor of 3. Now we're in a good position to solve through elimination. And we just do that by adding these together. Negative 25 plus 12 will leave us with a negative 13x. These two eliminate. Negative 15 plus 15 is 0, and we are left with 39 on the end. 0 plus 39. Finally, we just need to divide through by a negative 13. And we can determine that x is equal to negative 3. Well, what does it mean to solve a system? Have we solved a system? Well, if we're solving a system, we're looking at for the point of intersection. At this point here, we only have the x-coordinate. We need to find the y-coordinate. So hopefully you remember to take this x equals negative 3 and plug it back in. It doesn't matter which of these four equations we plug it into, because it's the one place where the two equations should equal each other. Let's go ahead and plug it into the bottom equation. So we have 4 times a negative 3 plus 5y equals 13. If we simplify this, we are left with negative 12 plus 5y equals 13, and then adding 12 to both sides, we get 25, and y is equal to 5. At this point now, we can see that we have one solution. These two equations, these two functions, and they're linear, will intersect at negative 3, 5. Okay, hopefully it's coming back to you. Go ahead and try this next problem, pause the video, and see what you can determine is the best way to solve this problem. In order to solve these two, because we have a variable y here that's isolated, has no coefficient, perhaps the easiest way to solve this one would be to use substitution. So what I'm going to do is rewrite this equation so that it's y equals. I'm going to move the 2x to the other side, so I'm going to write this equation in terms of x. When I do that, I'm left with y equals 1 minus 2x. Now I know what y is. I can take the 1 minus 2x and substitute that in for y in my second equation. Once I substitute this in place of y, all I need to do now is simplify the equation. I'll distribute the 2 into the parentheses, and then I will combine like terms. When I do that, what happens? These cancel, and I'm left with 2 equals 3. Does that make sense? Hopefully this is what you got and you were maybe confused, or you remembered that these two equations, if I were to graph them, will never intersect. They're in fact parallel, and that is why we do not have any solutions. Let's look at this graphically. Here I have graphed each of these equations in my graphing calculator, and you can see very clearly that these are two parallel lines. They must have the same slope, and therefore they will never cross, and there are no solutions. So this brings us to our next slide, our next question. How many different solutions can a linear system have, and what do these look like? Well, we just found out that we could have 0 solutions. And when that happens, we know that our lines are parallel. We also found that we could have 1 solution in the previous example. And when that happens, our lines intersect. Are there any other solutions that we could have? Well, what if we had the same line? What if we graphed our 2 lines and they were the same? How many solutions would we have then? In this case, because our 2 lines lie on top of each other, we would have an infinite number of solutions. Okay, and that's all our different types of solutions we can have with a linear system. But what happens if we have something that is not linear? So consider the linear and quadratic functions below. What are the coordinates of point P and point Q? This is another way to solve a system of equations. We can do it graphically. So if we look at this, though, it's difficult to see. We can see that our scale, this is 1 and this is definitely 2, but it's in between the 0 and this line here. So it might be a little bit difficult to estimate. We might say that this is a 1, so that this point is 2, 1, and we could be correct, but sometimes when we graph, it's difficult. How about this one here? It looks like 7 is right here in between this -6 and -8. And if we go down, well, 2, 4, 6, maybe a 7. It's hard to tell. So maybe this is a -7, or actually, this must go by a different scale since this is -10. So it's hard to tell. Maybe this is -8. So what we always want to do when we don't know for sure is to prove it algebraically. Let's go ahead and think about how we would prove this algebraically. Here's our 2 equations. Pause this video and see if you can prove what our 2 intersection points are, what our 2 solutions are. It doesn't matter if we have a linear system or a nonlinear system, we can still prove it the same way. Notice that y equals x minus 1. Well, here's why. We could substitute x minus 1 here in place of y and get one equation with just one variable. Anytime we have an equation with one variable, it's very easy to solve. We just need to simplify. The first step in simplifying is to take the x plus 2 and square it. So we would end up with x squared plus 4x plus 4. Remember, this is x plus 2 times x plus 2. Our second step is going to be to distribute the negative 1, basically, into the parentheses. Now that we've done that, let's move the x's to one side and combine like terms. I'm going to move the x squared over here, and then I'm going to add 4x to 1x to get 5x. Then I'm going to combine these like terms over here. -4 plus 17 is 13. I can see right now that I have a quadratic, and I will have to factor or use the quadratic formula perhaps to solve. So let's move the 13 over here and set it equal to 0. Remember that if you're solving a quadratic equation, it needs to be set equal to 0. Let's go ahead and see if we can factor this. When we're factoring a simple quadratic where we don't have a coefficient in front of the x squared, we can break it apart into 2 different sets of parentheses. So we have a binomial here, we have a binomial here. We need to ask ourselves, what times what is -14 that adds to be 5? And let's try a positive 7 and a negative 2. 7 times negative 2 is negative 14, and 7 minus 2 is in fact 5. So we have now factored this. Let's solve. To solve, we set each of these terms equal to 0. In this case, when we solve for x, we would end up with negative 7, and in the second case, we would have a positive 2. So now we know what the x terms of points P and Q are. This is going to be negative 7, comma something, and this is going to be 2, comma something. How do we find the y-coordinates? Well, again, remember it's the same way you solve linear systems. We can just take these and plug them in. The easiest equation to plug them into would be y equals x minus 1. If we do that, we can say y is equal to negative 7 minus 1, which is negative 8, which would be this y-coordinate here. And for our second one, we have y is equal to 2 minus 1, which is equal to 1, which would be the y-coordinate here at point P. So we have now proved algebraically what we thought about graphically. So now we've come to the end of our review of systems of equations. Now, what are some of the ways we can solve a system? We know that we can solve by substitution, by elimination, graphically as well. Is one method better than the other? It depends on what you're given. What does it mean when you're asked to solve a system? It means we need to find the points of intersection. And we've also answered the question how many solutions a system of linear equations can have.